Good evening, everyone. So this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. So this is a 12-week course, right? So we have just started this course. We are into week one of this course, and the theme of this week's content is basic thermodynamics and turbo machines. So basically, we have been introduced to basic thermodynamics and turbo machines in the three lectures of this week's content. So what's the purpose of these tutorials? So what we will be doing is we will be taking the lectures one by one, right? We will discuss the topics briefly. We will revise the topics that have been covered in the lectures, and based on a particular lecture, we will see questions. So this way we will conduct these, right? And the instructor for the course is Professor Vinayak Kulkarni. So he is affiliated to Department of Mechanical Engineering only as a professor here. And I am a research scholar basically here. So I am pursuing my PhD here at IIT Guwahati. All right. And my specialization, basically, I work on gas dynamics. I work on shock tubes. All right. So fluid dynamics basically is my specialization here, but I work on shock tubes. So we shall maybe wait for another few minutes. After that, we will start the session. Okay, so I believe we can start today's session. Right? So basic thermodynamics and turbo machine. So we have lecture, sorry. So we have lecture 1 and 2 on basic thermodynamics. Right? In lecture 1, we have topics based on basic thermodynamics, and in lecture 2 we have examples, numerical questions, solved numerical questions of your flow processes, right? Those flow processes are an integral part of this whole study of aircraft propulsion, right? Because later we will be discussing compressors, turbines, right? So flow processes is the basics of all these topics, basic of all these topics. So these are the contents of this particular tutorial. So first you will see topics of lecture 1, then questions based on lecture 1 and 2. Then we will move on to lecture 3 and then topics of lecture 3, and at last we will see questions based on lecture 3, right? So in lecture 1 we started with the terminologies, right? Terminologies like what is a system, right? What is a boundary, right? Terminologies like these, right? So system and boundary, I hope, is clear to you all, right? So this is very basic. The region that we are trying to study, right? The region we choose to study for our thermodynamic analysis, right? So that is basically system. And anything else other than that is comes under your surrounding, right? And what uh, differentiates or the boundary that is created between a system and surrounding, right? We call it boundary only, right? So how we separate a system from a surrounding, that is a boundary. Then different types of boundaries have been discussed, like fixed boundaries, right? Moving boundaries or imaginary boundaries. So all this has been discussed in your thermodynamic system. Then your types of thermodynamic systems have been discussed, right? So types are your open system, your closed system, right? Your isolated system. So these are fundamentals. I hope there is no doubt in these. If in case there is, you can always ask me. Right? So open system, what is an open system? What is a closed system? Right? So let's say we are interested in some system, right, in which there is one inlet and then one outlet. So what type of system is this? Is it an open? So we have a flow here going on. So this is inlet, this is your outlet. What type of system this is? Right. So this clearly this is an open system, right? So Lakshmana is saying that audio is weak. So is this with everyone? Someone can reply if it's with everyone. Audio is fine with everyone, or is it weak for everyone? Because he is saying it's audible. So maybe Lakshma can check whether the problem is from his side, right? So I was talking about this open system, right? So in case, so yes, for Siddharth it's audible. For Akshat it's blurry. So maybe you can check your audio devices. If for somebody it's audible, then in case whether this can be a network issue also from your end, right? For some people it's audible. In that case, yes. So so those who are facing audio issue, they can just check their either network issue or their device, right? Their sound device, whatever they are using. So I just talked about an open system. So in your closed system, whatever the matter you are trying to study, that uh, there is no in or out of that matter from your system of focus, right? That you are studying. So that basically is your closed system. Then is isolated system. So what is an isolated system? So isolated system basically is where there is no interaction with your surrounding of any kind, right? In terms of energy, in terms of matter, there is no interaction. That is basically your isolated system, right? Then is your properties of your system. So properties have been categorized broadly into one is your extensive and then one is your intensive. So what is an extensive property? Extensive basically is where the extent of the, sorry, should have been T, where the extent of matter decides the property, right? The amount of a matter decides the property, right? So we can, basic example is mass, right? Then also is volume, right? But then there are intensive properties also, which do not depend on your extent, right? So let's say we take a container, right, of 5 meter cube, right? Right. So we take a container, let's say of 5 meter cube, right? Then we take another container of 10 meter cube, right? And we define some temperature for this T1 and T2. So because your this container B is in terms of volume is greater than container A, doesn't mean the temperature will be high for your container B, right? The temperatures of both the of the matter in both the containers can be same, right? So in that case, the temperature becomes an intensive property. Right? These are basics. I hope there is no doubt or confusion in extensive and intensive properties. Right? Then is your thermodynamic state. So what is a thermodynamic state? So thermodynamic state basically is putting into perspective your thermodynamic system, right? When I say putting into perspective thermodynamics system, right? So when we are studying some system, so thermodynamic state. So when we are studying some system, so if we want to put things in perspective, right, that this in some system there is, let's say, some gas, right? So now I'm saying we want to put things in perspective. So how do we put things in perspective? We define its temperature, we define the pressure, we define the volume or specific volume. So all these things, by using all these properties, we are putting a system into perspective, right? So that is basically a thermodynamic state at a particular space or time, right? That is thermodynamic state. So based on properties, thermodynamic properties, we define a particular state, right? All right. Then next topic is your equilibrium. Then what is equilibrium? Equilibrium in very simple term basically is balance, right? So here we are. Propulsion basically is, it comes under thermodynamics only. So this is a type of thermal study, right? So here we will be dealing with thermal equilibrium. Okay. And why this equilibrium has been introduced? So what is the purpose of discussing this equilibrium? So this has been discussed in your lectures also. If somebody would like to quickly just in one line, somebody would like to say something about it. So why have this equilibrium has been introduced? Okay. So equilibrium basically is introduced because previously I said that I want to put things in perspective. For a system, I want a thermodynamic state, right? And to define a thermodynamic state, the system has to be in equilibrium. Only then I can define a state, right? That is why we are discussing this equilibrium here, right? So this has been discussed in your lectures, right? So that is the significance of equilibrium. So thermal equilibrium comprises of what? Mechanical equilibrium, right? Like, thermodynamic equilibrium, I should have said. So then thermal equilibrium and your chemical equilibrium. So when your system is in all these three equilibriums, in that case, we say that in terms of thermodynamics, it is an equilibrium, right? Then process, right? Next topic is your process, thermodynamic process. What is a thermodynamic process? So your system now is moving from one state to another state, right? So the process by virtue of which it changes its state from state, let's say from state 1 to state 2, right? So how this happens and what is the term in thermodynamics used? That is process, right? That basically is process. and from one equilibrium state to another equilibrium state if we want to go. Equilibrium state 2. In that case, we will have a set of states in between this whole process, right? So, and the path that it takes to change its equilibrium state 1 to state 2 has been called a path, right? So a path comprises of what? Different states. Okay. So this basically is your thermodynamic process, right? And what is a path? Then okay. Then types of processes also have been discussed, right? So in types of processes, reversible and irreversible processes. So all these have been discussed. I hope you all are well versed with these. So what is an isentropic, right? What is isentropic? Isentropic entropy, where entropy is constant, right? Where entropy is constant. What is isobaric? Bar is for pressure, where pressure is constant, right? What is isothermal? Where temperature is constant, right? Isochoric, where is your volume is constant, right? So these are types of processes. Then your laws of thermodynamics. So first is your zeroth law, then is your first law, then is your second law. Okay. Then Clausius theory and inequality, and then different cycles and their diagrams have been discussed at the end of this lecture. So what is your zeroth law? Zeroth law basically is what is zeroth law? So this talks about thermal equilibrium, right? If one system is in equilibrium with another system, right? Something like this. So if this is in equilibrium with this and this is in equilibrium with this, then A and B also will be in equilibrium. So this is your zeroth law, right? I hope there is no confusion in it. Then what is first law? So what is your first law? First law is energy conservation law, nothing more than that, right? Then there are equations related to based on your first law of thermodynamics that have been discussed. So equation for your cyclic process, for your non-cyclic process in a closed system, right? then your non-cyclic process in an open system. So these equations have been discussed in your first law of thermodynamics. Okay. So till this point, if somebody wants to ask something. All right. Nobody wants to ask anything. So then is your second law of thermodynamics, right? Second law of thermodynamics has been discussed. Right. Here, two statements are important. One is your Kelvin-Planck statement, then is your Clausius statement. So what are these two statements? These are fundamentals, right? Second law of thermodynamics, Kelvin's statement, Kelvin-Planck statement, and then Clausius statement. So both these statements talk about devices, right? So Kelvin-Planck statement talk about a device where from you have a higher heat source and then a lower heat sink, right? In terms of temperature, and it says that if we are giving in a cyclic process, if we are giving some heat, right, to some system, in that case, it is never possible that the heat we are giving to some system, the whole amount of heat will be converted to our work, right? So this is not possible. So 100% efficiency, this is not possible. This is your Kelvin-Planck statement. And what is your Clausius statement? So Clausius statement basically talks about your, you can take example of pump, right? Or refrigeration, right? So from lower temperature to higher temperature, right? We want the heat to transfer, right? In that case, we will need some extra work that has to be done on the system. Only then it is possible. Without this, this is not possible. This is your Clausius statement, right? So this is second law of thermodynamics. So Clausius theorem and inequality next is. So what is the purpose of discussing Clausius theorem? So this basically helps to decompose any reversible process, right, into your isotherms and adiabats. And this way we can then further study our cyclic process in small packets. So this is the whole purpose of studying this topic, right? Then Clausius inequality has been uh, mentioned and discussed, right? After that, your different cycles have been discussed, right? Your Carnot cycle has been discussed, which is an ideal cycle. Then Otto cycle has been discussed. The diesel cycle. Rankine cycle is used in your steam power plants. So if somebody is from mechanical background, they would know this. So all who are in this meeting from aerospace background, or somebody is from mechanical background? You can just type in the chat box if somebody is from mechanical background. Okay, so Mihir is from mechanical background. So he must have studied Rankine cycle. All right. And then Brayton cycle we will be using for our this aircraft propulsion studies. Okay. Then so this I won't draw all these diagrams. So this has been covered in your lecture. So at the end of this tutorial, if we have some time, we will see. Okay. Yes. So there are students who are from mechanical background. All right. And there are people from aerospace, obviously from aerospace background too. So that is great. Then lecture 2 is on your numericals on your flow processing, right? So nozzles have been discussed, compressors have been discussed. So we will see numericals, few numericals also. It's very basic questions I have on lecture 1 and lecture 2. So I want everybody to take part in answering, right? So we will briefly discuss then questions now based on lecture 1 and so let's see questions. So the purpose of these tutorials basically is that first you revise basically these your lectures, right, briefly, and then this should help you in your assignments also. So first we have this question. Try to answer this question. Yes, if you want to switch off your mics and answer, that is also fine. If you want to text in your chat box, if you want to use the chat box, that is also fine. Okay, so the first question says that the sequence of processes that eventually returns the working substance to its original state is known as dash, right? So the answer is cycle only. Okay, you people are right to answer this. So one example is of Rankine cycle. So last semester I was taking these tutorials for power plant system engineering. So we have there extensively discussed rankine cycle, right? So there we have water as working fluid, right? We convert it into steam, right? And then we pass it through a turbine, right? Then we condense. So after it passes through turbine, we have the required work output we have. Then we condense it, right? The same fluid, working fluid, that is water, we condense it, and then we further take it to pump. From the pump, we again take it to our boilers. From boilers, we then convert this water to steam. So this cycle goes on. So pump starting water from starting from pump eventually comes at pump, passing through your boiler from your boiler to turbine, turbine to your condenser, and then it again reaches to pump. So this basically is your cycle, right? So B is correct. Then question number 2. So your few assignments are not heavy on numericals part. So in your this assignment also you have, I believe, 2 uh, numerical questions. But then most of the assignments are heavy on your numerical part, right? This one is a bit on your concept-based questions or subjective questions, right? So this is question number 2. So I have discussed these different types of systems, right? Here, so here I was discussing this. I have given an example of a flow process, okay, with an inlet and outlet. So here mass is entering. So if we define this as our system of interest that you want to study within the dashed boundaries. Sorry, right? So mass is entering, mass is exiting, and this is an open system. Right? In your closed system, there is no entry or exit of mass. Same as with your isolated systems. So for your question number 2, the answer is C. Okay. So everybody has rightly answered this question. Open system. Okay, so this was question number 2. Then question number 3. So question number 3, it says that the cyclic integral del Q minus del W for a process within a closed system is. So people have answered 0 also. So those who have answered 0. So why this is option C 0? Somebody would like to discuss? From where is this answer of yours coming from? Yes. So this is from your first law of thermodynamics. So this means that if let's say we have some system, right? Closed system, because it says closed system. And we have, let's say, some gas here in this system, right? Right. So if your heat and work have to come into picture in such a system, right? In such a way that your whole process is cyclic. Okay. So it reaches its initial stage. After taking some path, it will reach its initial state, right? So in that case, let's say in terms of your EV diagrams, there's some, it was starting from here and then coming to again A, right? In that case, what will happen? So basically it is this, right? So this is your first law of, this comes from your first law of thermodynamics. So this will be the equation for your cyclic process. Okay. So C option will be the correct one. Then moving on to next, C is the correct option. Then moving on to your next question, question number 4. So please read this question and try to answer this also. Okay, so this question is based on entropy. The question says that which of the following is correct. So first says that for an isolated system, the change in entropy is greater than equal to zero. So it can be equal to zero or it can be greater than zero, right? So for your reversible process, your change in entropy is zero. So you must be knowing this that for reversible process, sometimes we say that if some process is adiabatic plus isentropic, in that case, that process is reversible. Okay. And what is isentropic? Isentropic basically is okay. So what is isentropic? Isentropic process basically is the one where we have entropy as constant, right? So the change in entropy is zero. Okay. So in that case, B is correct. For a reversible process, change in entropy is greater than zero. This is not correct, right? So this should have been for an irreversible process. Based on the answer I have, but that is fine. So people have answered A and B, so that is also correct based on the options that I had. All right. So by mistake, I have not correctly put the option C. In that case, option A and B are correct. Otherwise, if you, in your option C, if you take an irreversible process, in that case, your D option would have been correct. Okay, but that doesn't matter. What matters is that we should be clear about this question, right? And about entropy. So this was question number 4. If there is some doubt, you can ask, or there is one doubt in the chat box. So Garv Dharma writes that I'm in 10th class, aiming to learn about rockets. So if Garv is listening, Garv, are you there? You can just give me a yes if you're listening. Okay. So the thing is, the course is aircraft propulsion. So here we will be dealing with propulsion from the perspective of your aircrafts. Okay. And not from the perspective of your spacecrafts, right? Or for that matter, if you want to launch some satellite into orbit, right? So this course is not a rocket propulsion, but yes, a lot of thermodynamics or thermodynamic analysis, how you do thermodynamic analysis of a particular thermodynamic system. In this case, as far as this course is concerned, you'll be dealing with aircraft engines, right? Turbofans, turbojets, basically, right? And their components like uh, turbines, compressors, their blading. Okay, so somewhat in detail, these will be discussed. Rocket propulsion is another subject, right? Where you discuss about your solid rocket motors, then liquid rocket motors, and then their setup, all that. See, rocket science is the way combustion takes place in rockets. That is different science. All right. So that is another set of study when you're talking about rockets. So combustion here also takes place in aircrafts. Also, your aircraft engines combustion takes place. Combustion takes place in your rockets also, rocket propulsion also. But the fuel that is used there and how the combustion takes place there, that is all different, right? So that need to be studied in very detail, right? So these are different branches. Aircraft propulsion and rocket propulsion is different. So as a subject, I have studied rocket propulsion, and then aircraft propulsion also I have studied. That is why I'm telling you all this. All right. But you will certainly learn thermodynamic analysis here, right? And that can be of help in your rocket propulsion. That is what I can say. All right. So let's move on then. Suggestion, I'll have to see for your course for rockets or rocket propulsion. I'll have to see. But certainly, if you check the list of courses that are being offered by IITs or IISc Bangalore, so there will certainly be some course in some semester, right? Odd or even semester, monsoon or spring semester. That you also can check. All right. And if you want me to say, then I can also sometime do that. All right. So let's move on then. So this is maybe I can write my so this is my email ID. All right. Yes. Yes. Professor Sudarshan Kumar is from IIT Bombay. Yes. He works on he works on propulsion. I'm not sure about propulsion, but yes. If Mihir knows about this course, then you can just check this course. Okay. All right then. Next question. So this is a numerical. Please, first of all, have a look at this numerical and then we will solve it. Okay, so I'll just read this out. We have air at this pressure and this temperature, which is entering a diffuser. So what is a diffuser? So there are two devices. One is diffuser, one is nozzle. So nozzle, what does basically it speeds up your fluid, and diffuser is it speeds down the fluid, right? So that is a fundamental difference between a diffuser and a nozzle. Okay. Then so we have a diffuser with velocity this and leaves at a, so we have entry of fluid at this velocity and then leaves at temperature 310 Kelvin. Mass flow rate has been given this. Okay, the exit area of diffuser is given this, and the heat loss by the air is this. Then find the exit pressure and exit velocity of your respective. So these two things we have to find out: exit pressure and exit velocity. So let's do this numerical. This is your question number 5 and solution. So we have been given P1 is 92 kilopascal. Yes, my mic is on. Sorry. This is your 297 Kelvin. Okay. Velocity is 188 meters per second. So these conditions are at the entry of your nozzle, sorry, diffuser, right? You're discussing the diffuser. Then mass flow rate is given 3.2 kg per second. Then heat loss is given as -9 kilojoules per second. And what else we have been given? So for your exit, you have temperature given at 310 Kelvin, and then area also has been given as 0.035 meter square. Now, what we will be doing, we will be using energy equation. Right? So, as per your energy equation, so energy is from inlet and exit, we will be comparing. Okay, so this is for your, this caters to your inlet part and this to your exit part. Right. So now you have to give me the answers. You have to place the values and you have to give me an answer for what. So this can be cancelled from this. Okay. PP we have, P1 we have. So V1 we have. Do we have V2? We don't have V2. P2 we have. CP we have. This Q in, this is basically loss. So place this minus 9,000 equals to, now you have to solve this. So please find out first of all V2. So the value of V2 Akshat is giving me 60 meters per second. I have worked it out. So I have this. Okay. And then, so this is your velocity, right? Then you want to find the exit pressure. So exit pressure, how can we find out? So from your mass flow rate, okay. So if you see the given parameters, so this is your mass flow rate, right? Rho1 A1 V1 equals to rho2 A2 V2. Here density we have not been given, area we have been given, V2 we just found out. Now what is rho2? So this can be written as, rho can also be written as how? Like this. T equals to rho RT, right? Then A2 V2. Then this we have, this we have, this we have, this we have, this we have. P2 we don't have. Okay. So P2 now can be found out. So P2 is equals to, if you work this out, this comes out to be how much? If you can calculate this for me. No calculation? Yes, Mihir has answered. So others also, please calculate. Just give me a second. Yes, so 135.8. Yes, I have this answer. 135.8. The Pascal answer calculating. So this was your question number 5. Then this. Then next question. Next question. So we just saw a diffuser. Now we have what? Now we have a compressor. Okay. So a compressor is used to compress hydrogen from. So what happens in a compressor? So this is literal. It will compress some fluid that will pass through it, right? And what is compression? Compression basically is increasing your pressure, right? But with increase in pressure comes also increase in temperature also. That is another aspect of compression, right? So compressor is used to compress hydrogen. So we have hydrogen from this to this. Inlet area and velocity are this and this. So inlet parameters have been given and outlet velocity has been given. You have to find out mass flow rate and your exit area. You have to find out. So let's do this. Pressure and temperatures have been given from for your inlet and outlet. So one thing we can figure out that in terms of your density, if you write in terms of your pressure and temperature, right? So that you can get your density you can get from your pressure and temperature, because in your this continuity equation, in your mass conservation equation, basically rho AV, here rho you can get from your pressure and temperature, right? So this you can figure out from here. Then areas and velocities have been given. So this basically is based on your conservation only. But then we have to find out mass flow rate and then exit area. Two things we have to find. So first we'll write down whatever is given to us. Okay. Or maybe we can directly jump to your continuity equation. Okay. So whatever is given, we shall see that. Rho 1, A1, V1, right? Mass flow rate we have to find out. Yes, I have the answer. Okay. So this I have. Now pressure, yes. From 100 to 1000. So this is 100 kilopascal. R is given as 228, and then T is 298. Okay. Then area is 0.015, and initial velocity is in the compressor is this. So if you work this out, this is so what I have here is this value 0.22 kg per second. So you can just check your values where they have differed. Basically, you should understand that what you are doing. Okay, how you can find out these values in terms of some given values. In case you have some given values and you have to you want some unknown values, so how will you figure that out? That basically is the whole question, right? So if that is fine, in that case, okay. Then we need to find out the exit area, right? So from here, rho 2 we have, okay, V2 is given to us, mass flow rate we just found out, okay. So then is P2 by RT2 A2 V2 implies this. This. If you solve this, if somebody would like to give an answer for this. Yes. So this is 0.00136 meter square, sorry, or if you convert this into centimeter square, in that case, multiply it with 10 raised to power 4. Okay. So this is 13.68 centimeter square. Okay, so this is done. So these are the answers. Now moving on to next question. So next also I have a numerical, but before taking this numerical, I would like to move on to next lecture, I believe. the last lecture of this week, because we have around 35 minutes. So let's first discuss this, because we have already discussed lecture 1 and 2. So at the end, if we have time, we will discuss one numerical. Otherwise, this I believe will suffice. Or still, if you want me to at the end of the tutorial, if you want me to. What is SS? It's a screenshot, maybe. Okay. Yes. Screenshot you can take. So these videos will be uploaded on YouTube also. So from there also you can take. But yes, I can give you a screenshot at least of question. So this you can take if you want. These videos will be uploaded on YouTube also. So from there also you can take it. Okay, for your practice purposes. So I hope you have taken screenshot by now. I just want to lecture three. Okay, turbo machines. So the turbo machines. So this is basically the core of all the aircraft propulsion, turbo machines. Okay. So turbo machines have been classified in different types, have been introduced in lecture 3. Okay. First is your turbo machine, classification of turbo machines. Okay. Then types of turbo machines, positive displacement machines and non-positive displacement machines. Then your fans, blowers, and compressors. This. Then turbines and compressors. Then comparison between axial and radial flow machines. Okay. So usually we take a short break between in between after 1 hour passes. So we take one short break. So today we didn't take, but in future we can do so, right? So what are turbo machines? So turbo basically is if something is rotating, right? So the if you see the etymology of turbo machines, turbo, the term turbo, if something is rotating, it's linked to that. So that basically is your turbo machines. All right, then classification of your turbo machines. So one is your power absorbing, then one is your power producing. What is power absorbing? Your compressor. Okay. So your compressor, where you compress your air, you'll see in later you'll see the role of a compressor or a turbine in an aircraft engine. Okay. So turbine is from where you get your work output, and compressor is where you have to give work or power, right? So that is your in terms of power, right? Whether it's absorbing or producing. Then one is your extended turbine, right? Specification. So then there is one class is your extended turbo machine. One example of that is your hydrokinetic turbine, right? Basically, the in hydrokinetic turbine, what happens is your kinetic energy is only being converted into your this work output. So we are not taking help of the head pressure head. Okay, that is your extended one example of extended turbo machine. Then compressible flow turbines, right, where compressibility of the working fluid comes into picture. Okay, so if you see your compressors and your steam turbines, so when the your working fluid enters and exits, what is the scenario, right? So from that we can say whether your turbine is compressible or your incompressible. Your hydro turbines basically are incompressible, but the ones we use in aircrafts, compressors, turbine that will come in your compressible turbo machines. Then types of turbo machines. So two major categories are one is hydro, then is your thermal. Okay, so this basically is water based, right? And here the temperature in your thermal one, the temperature comes into picture. But in your hydro, the temperature does not come into picture. Okay. So the turbines that we use in hydroelectric power plants, that comes under your hydro turbo machines, right? In the same way, this further categorization of hydro and thermal has been done. Okay. So we will not go into that. So this broadly, this is it. Then is your positive displacement and your non-positive displacement machines. So what is positive displacement machines? your engines based on your displacement, right? So you take example of your yes, yes. So you take your piston engines, right? That comes under your positive displacement machines, and your axial flow machines, right? Like your turbojets, turbojet engine, turbofan engine, they are non-positive displacement engines, right? Or machines. Basically, that is the fundamental difference. Then there is a very good comparison between these two that has been done in lecture 3. So I'll not go into that. So briefly, I have told you this. Then is your fans, blowers, and compressors. So what is the difference between your fans, blowers, and compressors? So this basically is what? Based on the pressure rise that a particular device is giving to us. Based on that, we define these fans, blowers, and compressors. So if your pressure rise is within 2 psi, so we call it fan. If the pressure rise is between 2 to 10 psi, that is blower, right? If it is greater than 10 psi, that is greater than. PSI is your pound per square inch, right? So this is roughly around 6900 Pascal, if I'm not wrong. Okay, 1 PSI is this much, around this, 68 or 6900 Pascal. Between 6,000 to 7,000 Pascals is your 1 PSI. Okay, so PSI basically is a British unit, right? Not an SI unit. So, so this is your how you define your differentiate between fan, blower, and compressor. Fundamental is same, that you are increasing the pressure. Then what is there? Then is your turbines and compressors. So in turbines and compressors. So these basically they consist of blades. Okay. So blades, there are two types of arrangements. One is stator and one is rotor. Okay. So I would recommend that you see some video on YouTube of some turbine or aircraft engine, right? Or if you see of some turbine, that will suffice. Okay. So there you will have visualization of what is a rotor and what is a stator, right? So stator won't move. Okay. So these are, so there is one hub like this pencil, there is one hub, right? So around its circumference, you place blades like airfoils you have, right? The wings you have like in your airplanes. So basically, they are composed of airfoils, right? Airfoil is 2D and then this wing is 3D, right? So similarly, in that fashion only, so around the circumference, you place these blades. So here we call this airfoil structure as blade, right? So we place blades around this circumference. So one set of blades will not move. Then here one set of blades will be there that will move. Right. So this arrangement is seen in your turbines and compressor. Right. So then there is role of these. So these we will see in very much detail in the coming lectures. Right. But for visualization, I would recommend one video you must watch on YouTube, right? So this is your turbines and compressors. So you have some basic doubt on it, you can just ask. Otherwise, last is your comparison between your axial and radial flow machines. So axial is axial, radial is radial, very literal. Okay. So the flow, if you take this as an axis, right? So the flow will be in this direction. In that case, this is axial. If the flow is in this direction, right? In that case, it will be radial. All right. So this basically is your axial and radial flow machines. This also we will discuss very much in detail. Those are has discussed given the comparison of these axial and radial flow machines. Later we will discuss these in very much detail. Just at this point, you should know just basic of this. What is an axial or radial flow machine? This much will be, I believe, sufficient for you. But sir has given a comparison, so just have a look at that comparison also. Okay. Then questions. So in Brayton cycle, heat addition takes place at how heat addition takes place. I have not discussed Brayton cycle in cycles. So this is your question number 8, I believe. I'll just draw Brayton cycle. Brayton cycle, you should know, is used in your aircraft engines. Okay. Your non-PDM engines, like turbojet, turbofan. Here you use this. Okay. So your PV diagram here is like this. Something like this. This is your P, this is your V. P equals to constant here. Equals to constant, it's a straight line. Here entropy is constant, entropy is constant. Okay. For heat addition, in which part of your turbojet engine heat addition takes place? Basically, it takes place in your combustor. Okay. So which is, let's say this is 1, this is 2, this is 3, this is 3. So between 2 to 3. And this takes place at constant pressure, right? So this basically is your Brayton cycle. This much is fine. So there is TS diagram also, but let's not draw that. Okay. So in Brayton cycle, heat addition takes place at 4 options. B option is the correct option. Okay. Two-phase media. Which of the following cycles generally work with two-phase media? Rankine, Otto, Diesel, Carnot. Steam power engineering, two-phase, right? Water and steam. This is Rankine cycle. All right. Question number 9. Then question number 10. Please try to answer this. Question number 10. Please try to answer this. So which one of the statements are true regarding PDMs, positive displacement machines? So they have lower volumetric efficiency compared to non-PDMs, can only achieve compression through adiabatic process, can only be of reciprocating nature, involves low mass flow rates. So out of these 4, so their volume metric efficiency is low in comparison to your non-positive displacement machines, and involves low mass flow rates. Okay. So out of the 4 given options, in that case, C is correct. So while we are comparing PDMs and non-PDMs, you should also keep in mind that why this topic has been placed at the place where it has been placed. Okay. So why in our aircraft industry we moved from PDMs to non-PDMs? Okay, so that basically is the perspective. So question number 10 is this. Then question number 11. In order of pressurize, arrange these in ascending order of magnitude. So lower one will be the first one, higher one will be the last one. So the compressor is the higher one, that we for sure know. Then between fan and blower, let's see. So fan is lower than blower in terms of pressurize. So fan, blower, and then compressor. I believe B is the correct option. Yes, so B is the correct option. Then last question of today's session. Which of the following statements is true for axial and radial flow turbines? Radial flow turbines. Let's read the four options. So first is not a correct option. Now if you see B, mechanical strength of your radial turbines is higher, right? When you're in your axial turbines, you are connecting these blades with your this shaft, right? That because of that, your strength of axial machines is less, right? So this is also eliminated. Third is so connection of different components is easy in case of axial flow turbines or axial flow machines. Okay, because everything is straightforward. Later you'll see different components, how different components of a engine are arranged from your starting inlet to your compressor to your combustor to your turbine and then nozzle. But the fourth one has material. Okay, the pressure rise in radial flow turbines is much higher when compared with the axial flow turbines. Okay, so in that case, D is the correct option. Okay, so this is it for today. So I'll just briefly conclude today's session and then we will just end this meeting. Okay. So there were three lectures, basically lecture 1, lecture 2, and lecture 3. Lecture 1 was on basic thermodynamics, right? Where we saw thermodynamic system, surroundings, what is thermodynamic system, what is surrounding, what is boundary, what is the process, what is equilibrium, what is the path, right? What is the state of a thermodynamic system? So all this was discussed in your lecture 1, right? We saw its topics and then questions based on that. And then then we saw two numericals also based on lecture 1 and 2 because lecture 2 caters to the numericals of lecture 1 only. Then in lecture 3 was on introduction to turbo machines, right? There we were introduced to classification of turbo machines. And then what are the types of turbo machines? One is your hydro turbo machine. Then next is your thermal turbo machine, right? Then what is the difference between a positive displacement machine and non-positive displacement machine? Then we differentiated between blowers, compressors, all this, right? And eventually we saw what is the difference between these two axial and radial flow machines, right? And then we saw questions based on lecture 3, right? So this way we conducted our session number 1. Next session will be again on Tuesday at the same timing, 6 to 8 p.m. Right? So this was week 1's tutorial. So this way we will have 12 tutorials for 12 weeks, and at the end we will have one concluding tutorial also, session also, right? So in total we will be meeting for 13 such meetings. We will have 13 such meetings. So this was first one. All right. So this is it from my side. If you have something to say or share, then you are welcome. Otherwise, we will just end this meeting here. Okay. Okay, then in that case, thanks for joining.